let's start. Closing our virtual meeting, we have Topp from Universidad de Santiago de Chile. Thank you very much, Erin, for accepting give a talk in our virtual meeting in PDEs and applications. Erin will talk about Liouville theorems for non-local versions of the truncated Laplacian. Please, Erin.
Okay, thanks a lot, João, Vitor, for the introductions. Do you hear me well? There's a resonance phenomena. Okay. Okay, so thanks a lot to the organizers for the invitation. Very kind invitation. This is my first conference this year. I'm very happy to be here with you in this way. I have to say that this is the first meeting where there's exact the same number of women and men. So I'm very happy to see that, and I hope that this continues not only in the PDE community but also in the math community. Okay, what I'm going to talk today is a joint work with Isabel Pirindelli and Giulio Gallise from Sapienza University di Roma. And I will start talking about the second order counterpart. Usually in the non-local, okay, in some sense, non-local word follows the local word. Okay. So what is the second order truncated Laplacian? Okay, so we are going to consider a function u. We are going to compute the Hessian of this function u, and then we are going to consider the eigenvalues of the Hessian, order from the smallest to the largest, and we are going to pick only the last k, the largest k one. This is the pk plus. So the plus is because of the maximal, k is because of the number of eigenvalues where we're choosing, and maybe the p is because of Pucci, I think, okay, for extremal. So when k is equal to n, this operator is exactly the Laplacian, okay, because this is the sum of the eigenvalues of the Hessian, is exactly the trace of the Hessian. And it can be defined a similar way, the pk minus, which takes into account the smallest, the sum of the k smallest eigenvalues of the Hessian. Okay, but in this talk, okay, there are similarities, but also there are striking difference among pk plus and pk minus. But in this talk, I'm going to speak about pk plus. I'm going to concentrate on the maximal operator. Okay, so in some sense, direct consequence of the definition is that this operator, acting only on the, let's say, acting on the matrices, on the set of symmetric matrices, is a positively homogeneous operator. So if you multiply the, let's say x is the Hessian of the function. So if you multiply x by lambda, the lambda comes out whenever lambda is positive, and is degenerate elliptic in the sense that it's increasing with the in the order of the matrices. Okay, and I'm saying that n is positive whenever the eigenvalues of n are positive. It's positive definite. Okay, so it's degenerate elliptic. Okay, here is a non-exhaustive list of references that I'm going to present here. Maybe if you know something that is missing, please let me know. So this kind of operator appeared in the late 80s in some papers of Xia and Wu, Journal Differential Geometry and Indiana. And okay, I read a little bit the papers yesterday because to say something about that. And it's basically the following. You consider a manifold. Okay, you consider a manifold. I'm going to write a 2D manifold. You take a point P in the manifold. You take the tangent tangent space related with this is M, right? The tangent space, and then you compute the principal curvatures of the manifold at the point P. So basically, you take the normal, and you consider all the planes that are normal to TPM. So this, when you intersect the manifold with this normal kind of normal plane, so it is going to appear a curve here, and you compute the curvature of the curve at the point P, and then moving the plane, something like this. So you are going to obtain another curve. You are going to compute the curvature of that curve, and then you consider the maximal and the minimal curvature. These are the principal curvature. This, let's say, if you look at the Docarmo's book of surfaces in R3, this is exactly the definition, and then you pass to the Docarmo's book on Riemann geometry, and you can define the principal curvatures in a similar way. So then we are going to say that a manifold is K convex if the sum of the smallest K principal curvatures is positive. So I remember exactly, it's like saying a poem, something like that. So this is the first time that this type of operator appears related with the exponential map of the manifold and so on. Okay, and later this was, there are some papers of Harvey and Lawson, the last 10 years, something like that. This also arises in the context of mean curvature flow, Ambrosio and Sawyer, and because of the mentioned degenerate ellipticity, it was also considering the uses guys of viscosity solution as an example of degenerate elliptic operator. So viscosity solutions approach is adequate to deal with these equations involving this operator. And recently, there are some contributions by Birindelli, Galice, and Ishii in Poincaré, related with the principal eigenvalues associated to Dirichlet problems and this operator. And as Julio mentioned on Wednesday, there are some link between Dirichlet problems associated with this type of operator, not exactly this one, but I look at the paper of Julio and Pablo, where they mentioned that these extremal ones are also involved in their paper with the differential gains. In fact, there's a reference missing here, which is the paper of Silvestre Overman that Julio mentioned Wednesday, also related with the regularity C1 alpha results for P1, let's say, for the smallest. Okay, and I highlight this paper here of Isabeau, Giulio, and Fabiana Leoni in nonlinear analysis, where Liouville type results associated to this operator are in the scope. Okay. So basically, what I'm going to show now is that let's say the non-local counterpart of this paper. Okay? So as I mentioned, this operator is actually very degenerate in the sense that we always are going to find a direction where this operator degenerates. Okay, so roughly speaking, let's say in terms of regularity, Ishii-Lyon's method cannot be applied directly, or it is not possible to apply in a straightforward way. So there's a very open, standing open question related with the regularity of this type of operators that also Julio mentioned Wednesday. And the degeneracy of the operator, in fact, involves lack of strong maximum principle and Hopf lemmas and Harnack inequality. But for super solutions, we have strong minimum principle. This is going to be important. So we have, yeah, this is going to be important. It's a tool. This operator is degenerate. We have few tools to work with, but the strong minimum principle is at hand. Okay. Okay, so let me mention here the harmonic version of Liouville theorem for this truncated Laplacian. So if you consider an harmonic pk plus u equal to 0 in Rn, a bounded solution of this one. So if k is equal to 1 or k is equal to 2, the only non-negative viscosity supersolutions to these problems are constants. And if k is bigger than 2, there are non-negative classical supersolutions. Okay. Okay, let me explain a little bit what is in the heart of this result. Basically, what you do is the following: you consider a function which is radial, and you can compute the more or less easily the eigenvalues of the Hessian. So you compute the second derivative of u, you compute the Hessian, and there are two types of eigenvalues. Lambda 1, which is g second at R, with eigenspace x, so it's in the direction, I will call it the normal direction because it follows x. And the rest of the eigenvalues are g prime of R over R, with eigenspace the tangent to x, okay? The tangent space to x, okay? So for instance, what does this mean? This means that the fundamental solution, the idea is to construct fundamental solutions to deal with these Liouville type theorems. So in some sense, the fundamental solutions to PK are associated to the fundamental solutions of the Laplacian in Rk. Okay. So for instance, if you, in R2, the fundamental solution of the Laplacian is log of mod of x. So if you compute the first derivative here is 1 over R. If you compute the second derivative, it's 1 over R squared, right? This is going to be G. This is for k equal to 2, let's say. So the first one, this is going to be lambda 1, if you look at this one. And if you divide by R here, this one, you are going to get an R squared. You sum both of them, and then the sum is 0, okay? This for any dimension. So in any dimension, the fundamental solutions for PK is going to be the fundamental solution of the Laplacian in R2 for k equal to, okay? Okay, so then the cases where you have an unbounded fundamental solutions in the case k equal to 1 and k equal to 2. So for instance, for k equal to 2, you have that log of minus log of this operator, something like this, minus log. Is going to be the profile of the fundamental solution of P2 plus, okay? So here, okay, maybe until what time I have time to speak? Until Chilean time 12 past 11, no? Or 12 past 9 for you, João?
Do you have 26 minutes?
Okay. Okay, so once you have, let's say, I'm not going to go into the details, but morally, once you have an unbounded fundamental solutions, you have to reveal. Why? Because morally, what you do is to construct a function. Let's say U is the fundamental solution, the unbounded subsolution, unbounded subsolution, and then you construct a subsolution of the form. You fix up a number R1 here. Here you have your let me call V your supersolution. So you consider W equal the mean of B in the ball of radius R1, and then you put something like U of R minus U of R2 divided by U of R1 minus U of R2. So this is also a subsolution, but this subsolution is something like that. So it's something like that. So you have here something like that. Okay, this is R2, and then you put 0 outside. So this is a positive solution. So this quantity here is the mean. This head here is mean of B in the ball of radius R1. So in fact, this guy touches here. And as you can see here, I don't know if it is, you can see here, this guy is unbounded. So then you pass to the limit. When R2 tends to infinity, you pick this one and make this to infinity. So then this converges to 1. Okay, so then you have a sequence of subsolutions that are going to do something like this, something like this, something like this, something like this. So at the limit, V is above the minimum of the function itself in the ball of radius 1. So it should be at V. Okay, and here it is very important to have a strong minimum principle because we have a super solution that attains a minimum, so it must be constant. So morally, the existence of an unbounded subsolution, or subharmonic in this case, implies Liouville. Okay. Okay, but they go further and they study this kind of fully nonlinear, because this guy is nonlinear, semi-linear equation related with the pk plus, and they obtain this type of Liouville results for p less than k over k minus 2. So the only non-negative viscosity supersolutions are the trivial ones. For p bigger than k over k minus 2, there exist positive classical supersolutions for this equation. And then, okay, I think that Alex and Boyan spoke about these regimes also. This is called the Serrin exponent. This is called the Gidas exponent, and they also have some results related with the Gidas exponent. Okay, but I'm going to focus on the Serrin exponent in this talk. So what I'm going to speak about is on the Serrin exponent, Liouville type theorems with the Serrin exponent for a non-local version of this operator. Okay. I'm not going into the details about the proof of this, but morally, as oh, there's a mess now. There's a flavor related with the proof I explained here. Okay, maybe if I have time, I will explain. I will explain into the non-local problem directly. Okay. Okay, so I will explain the first version of this non-local operators. Okay. So there's no, or at least I do not know a notion of non-local Hessian, okay, or a non-local matrix, okay. So this is a problem. But in this paper, it is proven that the following characterization of pk plus for the local, the second order. So you take a frame, take a family, or take the family of orthonormal sets of dimension k. Okay, so if you are in R3, you take this one, but you can take any rotation of this one. I don't know. So all of them form an. They are orthogonal each other and have norm 1. You take all the families of this kind of operator, of these sets, and then you compute the Hessian, but in the direction of each of the components of this orthonormal. I think this type of sets are called the Grassmannian, the Grassmannian of dimension k. So you take all the possible Grassmannians of dimension k, you compute the second derivative, the quadratic form in any direction, and then you sum. Okay, you take the maximum and then you arrive to the same operator here. So this guy is exactly the sum of the largest k eigenvalues of the Hessian. Okay, and in the same way, replacing this max by this mean, by a mean, we have the minimal operator. Okay. So then I met Julio and Isabel several times in several congresses, and they say we have to work each other. So I look immediately at this one, and then I say, okay, this can be done in a nonlocal way. So we suggest the following definition, this one. So I changed the name from P to I. So I is because of integral, okay? So I will pick exactly the same formulation as before, but instead of computing the quadratic form here, I will consider, let's say, one-dimensional fractional Laplacians. So I will compute one-dimensional fractional Laplacians in the direction of each component of the Grassmannian, and then I sum, and then I take the max. So this is going to be the maximal operator. Where, as been mentioned in several talks this week, let's say the fractional Laplacian in dimension 1, as you can see here, is defined in this way with the principal value here. But if you look here in the definition, Xi in the components of the Grassmannian determines the direction where we are looking at in Rn, in some sense. So in this talk, we concentrate. In fact, in this work, we concentrate in the let's say the diffusive regime. So S is bigger than 1/2. So it's closer to the local case. Okay? So because of the structure of this operator, so we have that this enjoys comparison principles. It's a sort of non-local degenerate elliptic operator, and we have also strong minimum principle. Okay, this is work with of Xiumaga and the foundations of the non-local, the viscosity theory for non-local operators in Varl and Poincaré. And in the same way, can be defined the minimal operator, I minus k, replacing a minimum here. But as I told you, I'm not going into details about this operator. I'm going to concentrate in the maximal. Okay. So okay, maybe later if we have time, we can discuss about the validity of this one. But let me go into let me discuss about this. Okay. So of course, in order that this guy is well defined, we need first regularity condition of u at x, because this can be singular, it's too singular. So in order that this is well defined, we need that this guy compensates this one. So we need a regularity condition of u at x, but also a growth condition at infinity. Okay, so through this talk, I'm going to assume that everything goes well. Okay, so this guy is always well defined. And for computations, it is useful to get rid of the principal value. So there are several ways equivalent ways to do that. But what we have chosen in this work is this form. Let's say this looks at this is the, let's say, the finite second order difference of u in the direction of c. So in order to compensate the singularity of this guy here, we need to look at the second derivative of u, okay? And in fact, when we pass to the limit as s tends to 1, this kernel is very singular. And this constant cs in front allows us to pass to the limit, and we arrive to the second order operator, okay? So this is compatible. At least this is compatible when s tends to 1. Okay, so we arrive to the extremal truncated Laplacian, second order. Okay, so I like to draw. Let me do some drawings about this. Okay, of course we want Liouville theorems. To get Liouville theorems, we need fundamental solutions, and the nicest way to explore fundamental solutions is through radial solutions. radial function. So imagine that u is radial, okay, for the moment. Okay, so then imagine that you are here, we are in R2. Okay, this is R2, this is X. Okay, this is X. Okay, and then consider a radial function. So a radial function, sorry, I'm a little bit nervous, so the circles are not so nice. So the level sets of radial functions are circles. So then, if you, for instance, if you take this side, I will choose only one side. If you choose one side, what does this integral see? I will write the principal value formulation. So u of x plus tau c minus u of x tau to power minus 1 plus 2s. Okay, dito. Let me concentrate in this formulation. So what does this integral see? See, this is I insist, this is a one-dimensional integral. So what this guy sees, okay? So what does this guy sees? I will put, this is the word of tau. This is the word of this integral. Okay. So here I will this u of x when tau is equal to 0. When tau is equal to 0, here this u of x minus u of x is 0. So the value of the function of the integral at tau equal to 0 is this. Okay. And yeah. And if I go when tau is minus tau, when tau is minus mod of x, so this is minus mod of x. When tau is minus mod of x, I go exactly to, this is 0, right? So imagine that this is the u of x is g of mod of x, and g is something like this, a Gaussian if you want. So that's a maximal at 0, okay? So then I will have here, when tau is minus mod of x, this is g of 0, which is maximum, minus u of x is minimum. This is less than this one. So here it is positive. Here it is positive. So and so then this is when I am this is, sorry, c is equal to this one. So I go from tau equal minus mod of x, I arrive here, and I look the maximal here. So it's something like this. So the integral looks something like this one, and goes down, goes down, goes down. Is 0 when tau is equal to 0. When tau is equal to 0, is u of x minus u of x, so it's 0. And if I continue when tau is positive, and the profile of the radial function is decreasing, then the values of the function outside this ball of radius r is going to be less than u. So this value is going to be less than u. So here is going to be negative, something like this. Okay, and then continues in that way in this for infinity. This is the integral. This is the integral, and you have to take. Okay, what I wrote here is this contribution, this function on tau, but there's this kernel here that this is the protagonist, let's say, of this guy. So you must take into account here. So here this the kernel. This is tau to power minus 1 plus 2s. So in some sense, when you try to compute this monster here, you have to take into account the contribution of this, let's say the finite second order difference times the kernel. So looks a lot of what happens around x, in fact. Looks a lot, because it gives a lot of weight to this one. So when you pass to the limit as s tends to 1, in some sense concentrates here, and this is why you look at the second derivative when you pass to the limit. Okay. Okay. I hope this is not so confusing. Okay. On another drawing, let me do another drawing. What happens if you look at this direction now? Let me change it. What happens if you look at this direction? Then the tangent one. So if you look at the tangent one, what does the integral c's. So what does the integral c? Is 0. 0 is when you evaluate tau equal to 0 here. So you have this line here. So when tau is positive, so it's symmetric, completely symmetric. And if you look here, we are far away or more far than the points in this line here, compared with 0. So when we have to look at this profile, so this is decreasing. So this is going to be something like this. What does this integral c's in that direction, the normal direction, is something like this, right? So it's negative. In that direction, we are sure that this integral is negative, let's say. And then you can play the game with any direction, psi. Okay. Okay, I'm sorry for this. So, oh my God, I have 10 minutes. Okay, so we have this set of properties. Basically, what does this mean? Basically, so basically, what you have is that if you have x here, you can take the terms in the Grassmann. You always can assume. Okay, you always can assume that the x's in the definition of the operator here have angle less than pi over 2. Okay, and in fact, because of this set here. I'm sorry, I have to wait till this appears. Here, there is a lot of symmetries here. So if you change c by minus c, this is c equal. There's some rotation invariant. We can't if I have x here. This is the x perp. If I compute the operator in this direction, it's exactly the same as computing in this direction. Let's say the reflection with respect to the tangent space. And is invariant under the rotation, leaving x invariant. So the value of I of c of u at x when u is radial is the same in this cone. Okay, so there's a lot of symmetries. So this allows you, in particular, to without loss of generality, assume that the Grassmann belongs to the canonical vectors in Rn. Just moving x. It's very good to compute things. Okay. So let me pass to the results. Some results. Okay. So imagine that I will draw a lot now. So imagine that u is something like this, and radial, of course. Okay. So then the maximal. When k is equal to 1, when you need to choose only one, the maximal direction is exactly in the direction of the normal, and the minimal one is in the direction of the tangent. Okay. Basically, the proof is the following: you have x here, this is x perp, and then you take a vector here. You say, okay, this is psi of theta when theta is this angle, and then you compute this. You can compute this explicitly, you can write it explicitly, and then you take derivative of this guy, and then you prove that the derivative is negative. So the maximal is here, the maximal is here, and the minimal is here when you move this guy here. Okay, this is basically the proof. I'm sorry, I have to rush now. Okay, now what about k, larger k? So when k is larger than 1. The best choice of what does the extremal operator sees takes one direction, the direction of the normal, so looks at the direction of x, and the rest of the other guys are going to be in the tangent space. Okay, we have strong assumptions on G, but these assumptions are satisfied by power type functions. Okay. Okay, so this proof is not completely obvious. Why? Because if you have now you have to move two directions. at least a two-dimensional frame. Okay, so if this is X, and then you have a two-dimensional frame, because this is C1 and this is C2, we know that as the smallest is this angle, largest is the value of the operator when you take a G, let's say a decreasing power, okay? So, but if you move, let's say if you move in this direction theta, okay, you are going to decrease with this one. So the contribution in the sum is going to be decreasing this one. But if you look at the reflection property, so this angle, this guy here, exactly this let's say theta tilde, is going to be like this. So if this guy moves, remember that this guy and this guy always have to be orthogonal. So if you move in this direction, because of the reflection property, this is going to be increasing. So it's going to diminish the angle. So it's a kind of competition. This diminishes, but this increases. So it is not completely obvious how to do it, but you can still prove that the best choice for IK plus is this, chooses the normal one. So once we have this, we can compute, we can obtain the first Liouville theorem for harmonic functions. So contrarily to the local case, only k equal to 1 admits, or let's say in the opposite way. For the local case, k equal to 1 and k equal to 2 implies Liouville. I mean, there's no non-trivial super solutions, okay? But in this case, only for k equal to 1, we have no non-trivial super solution. And this is morally is because we diminish the we have diminished the order of the operator. So in some sense, k equal to 2, the dimension k equal to 2, in some sense is too large for the order of the operator. Okay, this is a striking difference with respect to the local case. Okay, how do we get this? We construct fundamental solutions for k equal to 1. This is a very straightforward adaptation of a result of Guy, Manusha Sen, Christine Georgelin, and Espen Jacobsen. And once we have the same spirit as I explained at the beginning of the talk, once we have a unbounded subsolutions, we have Liouville. Okay, and this is only possible when k is equal to 1. And for k bigger or equal than 1, what we do is the following. We compute the extremal operator in a negative power function, okay? So because of the homogeneity of the operator, in some sense we differentiate 2s times, and the constant ck in front depends on gamma, the exponent of the power, and it's divided in two parts. Let's say the normal part and the tangent part because of this characterization here, okay? So we have two constants that compete. So the normal one is positive because in some sense it looks at the convexity, and the tangent one is negative because it looks at the first derivative, the decreasing behavior. But how does this look, this constant c in terms of gamma? How does this look, this constant ck in terms of gamma? Looks like something like that. This is gamma, looks like this, something like this. It's strictly convex, is 0 at 0, and goes to plus infinity when gamma tends to 1. Because when gamma is equal to 1, this is not integrable in 1D. So there's a lot of mass. So there's only only gamma bar that there's only one zero of this function k that allows us to construct a fundamental solution. Okay. Okay. What happens? What is very strange? It's not that strange because it is a set of k1D integrals. Okay. So gamma bar is confined to the set to 0, 1. Gamma bar, the zero, the exponent of the fundamental solution for IK plus, belongs to 0, 1. And moreover, we did very large computation with Julio in my days in Rome, that when you compute this C2 in 2 times 1 minus S, this is positive. So 2, 1 minus S is in this side of gamma bar. Gamma bar is something very difficult to compute. And then when S tends to 1, this pushes gamma bar to be 0. So gamma bar tends to 0 as S tends to 1. This is a non-local phenomenon, let's say in that way. It's a very, very non-local phenomenon. And we were very disappointed at some point, because in some sense we cannot arrive to the critical exponent for the Liouville, to the semi-linear Liouville theorem when we pass to the limit as S tends to 1. But this is because of the definition of the operator. Okay, so since gamma bar tends to 0 as S tends to 1, the P tends to infinity, and then we do not arrive to the exponent of the local case. Okay, so if you give me, are you tired? If you give me 2 minutes, I will skip the proof. This is based, in order to quote the people, this is based in a paper of Fermer and Quas, okay, the Liouville theorem here. If you give me 2 minutes, I would like to only show you the second version. So in the second version, the only difference, the striking difference, in fact, is that the integral defining we are going to take an extremal operator of linear functions or linear operators, but this time the operators are like the fractional Laplacian dimension k. Okay, this is the difference. So we take the Grassmannian, we take the span space, associated to this Grassmannian, and then we compute the integral in dimension k. Okay, so this there's a lot of difference. So look at this. This J1 plus operator is exactly I1 plus or minus operator. It's exactly the same as before, because we have only one dimension. And when k is equal to n, this is the full fractional Laplacian, so it's linear operator. So the interesting guy is when k is between 1 and n. And similarly to what we did in the previous case, we have that extremal looks at the normal direction, and the minimal one looks at the tangent directions. Okay, so in particular, as a corollary, if we concentrate in JK plus, the JK plus is basically the fractional Laplacian in dimension RK, in RK. So it's very more similar than what happens in the local case. And in fact, using that the fundamental solutions of the fractional Laplacian in RK are power type functions for 2s minus k, x to 2s minus k. For the Liouville theorem, for the second version of the operator, we arrive to the Serrin exponent when s tends to 1. Okay, so now this is my last. I'm sorry to use your time in this last part. So the discussion is open. Which is the best operator? Let's say. Thanks.
Thank you very much, Erin, for a very nice talk. Questions or comments to Erin? I have a simple question. Could you change the p power for a very general convex function with a suitable growth at infinity at the origin?
We did not explore that that way, but I have to confess that what we have relies heavily on the homogeneity. So I think a different approach is needed.
Okay, Erin, thank you. More questions or comments? If not, thanks, Erin, again for the very nice talk.
Thank you.
Finishing this event, if possible, I would like to take a event photo. Then, if possible, turn on your camera. Then Leandro del Pezzo will take the official photo.
But give me a second, please. You need to stop. Okay.
Okay. Let me.
What can I do? Erwin. Ahí está.
Hey.
Thank you. Give me a second. Okay.
Turn on your camera, please. Everybody. The official photo.
I am sorry, I no longer have my camera.
Okay.
Comes the baby.
One. ¿Estamos todos?
Creo que sí.
Okay. I don't know what this word, but okay, again. Give me a second. This is very difficult, huh?
Very difficult task.
Yes, I don't know why you want to do this. Okay, again. Perfect. Thank you.
Perfect.
Thank you.
Thank you,
Thank you
guys.
very much for everyone.
También vas a tener
And clap now.
Bueno.
Okay.
Bueno, aplauso a todos los oradores y a los organizadores. La verdad
Gracias.
que
Fue el congreso más fácil de organizar.
No, mucho laburo en casa. Mucho
Sin
laburo en
café,
casa.
sin plata, ningún problema.
Bueno, tengo que agradecer a todos los speakers, porque sin el soporte de ustedes el evento no sería posible. Un saludo especial a Julio, María, Juliana Fernández, Hernán, Jacqueline, Irineu, Alexandre, Mariel, Begoña, Joana, Boyan y Erin. Muchísimas gracias por todo.
Gracias a
Sí,
ustedes.
lo organizamos
Gracias
todo
a
volando y todos nos
los
dijeron
participantes.
muchas gracias.
Nos debe
Gracias a
la
la
cena
audiencia.
social. Social
Sí,
dinner
obvio,
is
el
missing.
asado, el asado. Julio lo hace. Hay que conseguir
debe,
una
lo
parrilla a
debe.
Julio y Julio lo hace. El asador oficial del congreso es
Y
Julio.
Julio lo hace.
yo estoy esperando el vino, no llegó acá todavía.
Bueno, yo voy a agarrar mi vaso. Hagan lo mismo y nosotros brindamos.
Oye, os dejo que pierdo el avión. Chao.
Sí, Neo, cuídate.
Igualmente. Chao.
Bueno, chao, chao.